Hello everyone. This video is about design of a milliohm-meter. There are a lot of videos on YouTube that talk about milliohm-meters, various versions, simple ones to more complicated ones, and I decided to make my own, getting some ideas from different sources, and this one is the first attempt of doing that. So let's look why we need a milliohm-meter. Anytime you want to measure low resistance components accurately, such as wiring, shunts, transformer windings, anything that carries high currents, for example, typically will have low resistance, so you want to measure those. General purpose multimeters don't have the requisite precision or accuracy to measure anything below a few ohms, even worse when you have a two-wire measurement. Lead resistances in the meter itself can introduce large errors when measuring small resistances. A milliohm-meter typically will have 4-wire Kelvin leads, which mitigates this issue. And lastly, if you try to do it indirectly by pumping a lot of current to the device, like into the device in the test, it will usually heat up and it will increase the resistance, most likely causing errors. So you want to avoid these kind of problems. So the specs for a milliohm-meter, what are they? Range 0 to 10 ohms, resolution 0.1 milliohm or better, accuracy I want it around 1 to 2%, power typically low power DC 9 volts input, and some unique features like no need for zeroing the meter, one-time calibration only using a standard resistor, and it should read directly in ohms, not in some fraction of like tenth of an ohm or something you have to multiply out. So I wanted to make it very simple to use. Conceptually, milliometer is fairly simple instrument. Basically, you need to send in a constant current into a unknown resistance, which is the device in the test, and you measure the voltage across it. But practically speaking, it's the accuracy issues that come into play when you measure small resistances. So I'll go over some of the blocks here one by one. Starting at the top left, there's the main current mirror, which is driven by a 1.25 volt reference. The current that comes out of the current mirror depends on the load resistance it's driving, which is in this case 12.5 ohms. 1.25 volt reference develops that across that resistance, which creates that 100 milliamps. So together, these three blocks create the main accurate current source and resistance to create the 100 milliamps. In my case, it's not doesn't have to be precise, but that's how I design my block. So I'll explain why I don't need an accurate current source. Finally, at the bottom left is the resistor under test. And there's two inputs, the current inputs that drive the 100 milliamps into the resistor, and the two sense outputs are the voltage measurements that carry no current, and so therefore there's no voltage drop in those leads. A simple milliometer that you find many implementations of on the internet, they basically use the reference with a load resistance and send an accurate current into the resistor under test. That works very well because if you can measure the current accurately, then you don't have any gain issues and you don't have offsets in the amplifiers, and it's pretty much a very robust solution to do that. But this version I decided to do something a little bit more interesting. I've seen some implementations such as this before, where you put in a gain of 10, which then basically means that if you have a 100 milliamp source, which is a good amount of current that you can send into a resistor without overheating it, most likely for a low value resistance, then you can actually get a direct voltage reading for a given resistance. So if you have a 1 ohm resistor, you get a 1 volt reading. To get that, basically the equation shows that the voltage is equal to the current I times the gain of the amplifier times R dot. So given that we have 0.1 amps, gain of 10, ideally you should get a 1 volt output. So there's no mental conversion required, such as if you have a gain of 1, of course you're going to get 100 millivolt output for a 1 ohm resistor, which it can get confusing with many different values that are not so simple to evaluate in your head. Anyway, so this is the approach I took, but the only issue is going to be the fact that you're going to have offsets in the amplifier, and most likely you have to adjust the gain. So you got multiple issues to deal with in terms of accuracy beyond the 100 milliamp current that you can tune. So the approach I've taken here is to basically use an instrumentation amplifier followed by an offset correction circuit that is run by a clocking circuit. I will get into that a little bit later. So essentially I'm sampling the offset inside the instrumentation amplifier and then cancelling that out. So that should be working well if you can do that. And with this approach, basically you can essentially do a single calibration for gain, and assuming that the offset cancellation works very well, you don't have to do any zeroing. So the auto zero function is built in into the circuit. The other advantage of this technique is basically you don't worry about any inaccuracy in the 100 milliamp or the reference current. It may be anything, and you can set it to any value you want, maybe 50 milliamps, whatever is convenient. And even the gain resistors in the instrumentation amplifier, where there are several of those, you don't have to worry about those. They can be mismatched as long as they don't vary over time, or due to temperature drift in any way. And so therefore you can use one gain calibration given a known resistor or a standard accurate resistor, and you should have an accurate reading from this instrument. Any offsets that are time dependent are cancelled by the offset cancellation circuitry, which is running continuously. So any temperature drift or voltage drift or any power supply related issues are all cancelled. So that's the main advantage of this technique, is you need a single point calibration, and you don't have to worry about zeroing the meter every time you use it. I'm not going to say too much more about this circuit at this time. I'll probably release the entire schematic at a future date. Basically just an instrumentation amplifier with an offset correction loop using a clocked, like a switch capacitor if you will, or a sample system. So that makes it periodically calibrated, periodically offset calibrated. So in that sense, it's robust. You can also, I'll talk a little bit more about that clocking for that in the next few slides. So the offset calibration requires another op amp, which is part of the instrumentation amplifier loop, and it requires a clock. So with those two uh, uh, components, we can basically cancel offset. The only requirement is that the offset cancellation amp has to have low offset to begin with. That's the only offset that cannot be cancelled out. So we would need to use a good op amp for that one, which low offsets, which are easily available right now. Now we can talk about the power supply requirements. I have an external 9 volt input coming in, not 12 volts as shown in the picture. That's an error. And I have a voltage doubler IC that doubles that input to plus minus around 8.5. There's some drop in that regulator circuit. And also I need a 5 volts output for some of the op amps there. So plus minus 9 or plus minus 8.5 and a 5 volts, and the total current is I believe in the order of 10 milliamps quiescent, and when it's measuring it will probably be around 110 milliamps, because the 100 milliamps basically flows through the resistor when the circuit is energized, that is when the R dot is connected to the circuit. The next block is the display unit, which is not part of this board and it's not designed in. Basically I drive the analog output to either a multimeter or to an external dedicated voltmeter, which can display this in 4.5 digits or 3.5 digits, whatever is available. So I didn't really spend much time except to show this in the schematic or in the block diagram to indicate that there is a display requirement, of course. So for the prototype I decided to use my handheld multimeter or benchtop one, just to show that it's working well, and I didn't want to introduce any additional offsets from the external voltmeter. So to conclude the presentation of the block diagram and to highlight the main features, there is no offset or zeroing requirement required for this milliohm-meter. It's very easy to use that way. There is only one-time gain calibration using a standard accurate resistor like a 1 ohm or whatever value under 10 ohms that you can find, and that's all you need. And the third is that you don't need accurate resistors or accurate currents because you're going to be calibrating for against that accurate or standard resistor one time, and any offsets or any drift are basically taken care of by the circuit itself. So this is what the initial prototype looks like. It's not very big, a few inches, maybe 3 inches by 2.5 inches or so roughly. There are 4 leads for the measurement of the resistor, basically Kelvin type of clamps or Kelvin leads. There's a power supply, which is external 9 volt DC supply coming from an adapter from the AC, and 2 leads that go to an external multimeter. In the future, as I mentioned, you could put in a display for this thing. So next, I'm going to show you a little bit zoomed in view of the entire board, and I will go into some of the sections within this board to show where the components are placed. So this is the voltage reference and the current source, the 2 top left chips, and below that is the actually a 50 ohm resistor, 4 of them in parallel to create roughly 12.5 ohms. I have a 1.25 volt reference. Below that is the leads for the resistor themselves, the sense and the force current leads. So it's a 4 terminal measurement. And this one is the amplifier section. I have some switching going on in there. And the blue potentiometer is the gain calibration resistance potentiometer. So that's the one-time calibration or tuning you need to do. Top left shows the power supplies, the voltage doubler, a 5 volt regulator, and some filtering caps. Fairly straightforward. And that section over there is the the offset calibration along with the clocking circuit. The frequency of the clock can be adjusted using the upper potentiometer. Not very critical, but I typically would like to update the offset every second or so, or even slower if you can basically program that as you wish. Here we have a setup doing a measurement of some resistances. Currently I've connected a 3.3 ohm resistor here. It's a fairly large, I think 5 watt resistor if I'm not mistaken. I'm going to measure 3 of them and show you the resolution of this thing. So right now I'm measuring 3.249. It's supposed to be 3.3. Let's do another one. So the outer red and black leads are the force current, and the inner ones, the white and the yellow, are the sense voltage measurements. So this one reads 3.2580, and the last one .2525. So you can see that the resolution is 0.1 ohm, milliohm, and it's fairly able to distinguish these 3 resistors down to the milliohm level or 100 of micro-ohm level. So one of the things, if you notice, is that this you'll see the display momentarily change for a short time. That is due to the offset cancellation circuitry. If the offset is large, it may take a while to settle out, but right now it seems fairly stable, not moving around that much. So I'm going to another resistor, smaller value. Let's try a 1 ohm resistor. The nice thing about using these 4 wire thing is that you can clip the source anywhere you want, but you have to place the sense where you think you're going to want to measure, depending on how short the leads are. So it gives you some flexibility in that sense, if the part is not accessible that well. So this is a 1 ohm resistor, and this one reads 0.9064, roughly 9063. So I don't know the actual value of this. I plan to do another measurement with a different meter to confirm what the value is. So it will vary slightly as a thing heats up. Ideally, this will be used to measure very low resistances, which typically conductors that carry high currents, so the self-heating effects will be fairly small. But in this case, if I use very small components, yeah, you're going to see some heating effects. Unfortunately, using 100 milliamp current, that's what you get. That's one of the disadvantages, but at the same time you have better noise performance in the measurement and less gain required, so that helps. Now this is a 0.1 ohm resistor. This is going to have more self-heating, but if you do a quick measurement, it's probably okay. So there you get 0.10175. So as you can see, the meter is accurate, and it actually, I'll have to confirm that, but it's got high resolution, at least for now, and it can distinguish down to the hundreds of micro-ohms or even smaller. And you'll see the effect of measuring at different points. The lead resistances, in this case, if I measure over here at the right where the source is, you'll see a distinctly different value, and that is 0.13056. That means there's a 0.30 milliohm of extra resistance just in the leads going from here to here, 15 milliohm on each side. So these kind of resistances can play a role if you're not, if you're really trying to get down to the milliohm level of measurements. For fun, I'm going to measure the resistance of this steel ruler and see if we can get that. So it says 15.95 millivolts, so that's 15.9 milliohms. As you can see, it makes very tiny resistance measurements. If I move the position to somewhere in the middle, the resistance is now 3 milliohms. So as you can see, it makes a difference where you measure, of course, since this is acting like a long resistor, and you get 8.7, 8.8, 9 milliohms. So yeah, this can be a very useful instrument, and you can of course measure heavy wires down to the milliohm level. So that's the demo of this unit. Next steps is to remove some of the artifacts I have with the offset cancellation, which requires an additional sample and hold stage. I was thinking of also putting in a second range, which would not be as accurate as the milliohm range, but will increase the flexibility to measure up to 10 kilo ohms. This one has a limit of about 8 ohms because the supply goes to plus minus 8 volts. So for me, an 8 ohm resistance full scale for a milliohm-meter ohm meter is a good compromise for measurement of low value resistances. Anything higher, I can use a benchtop multimeter or even a handheld, which can do better jobs in the tens, 100 ohms, and even higher. I will of course go back and check the resistances I just measured on this video using an HP4328. My friend has one. Borrow that and put down those values somewhere at the end of the video. So want to make sure I close the loop on that. So thanks for watching. I hope this was enjoyable. Hopefully I can provide more information as I wind up this design completely. So see you another time. Bye bye.